So, hi, and welcome to our talk, Stream Processing Rocks.
Hi, my name is Hunter Sherman. I'm a distributed systems engineer. I've been writing Kotlin for almost 8 years now.
And I'm Jeff. I work with Hunter as a pipeline engineer too, having recently returned from a turn at management. I'm a Kotlin enthusiast, a reformed poet, and a fan of bad metaphors. We're going to talk about streaming applications. Who was at the talk earlier about Kafka and Flink? Okay.
There'll be a lot of similarities.
Yeah. Who's already using Kafka Streams? Okay. All right. Well, we'll be working at a lower level than Flink, but a lot of the ideas are the same. Might start out a little slow for all y'all experts, but let's start with looking at what makes stream processing great. Or maybe let's start with what streaming applications are not. A common application model centers around a database. An API service writes ingested data directly to a central database, often after some amount of analysis and transformation. Another service or set of services will transform the new records by loading them out of the database, processing them into some novel form, and then writing some new something back to the database. The primary limiting factor of this design is its dependency on that central database. Polling also presents some scaling challenges. So this application does not work, or application design does not work very well for our problem domain. We work on observability tools at SolarWinds. We develop data pipelines for high throughput telemetry data. When I say high throughput, I mean about 1 million metrics a second, 200-ish megabytes of logs a second. We're still very early in the product's life, and those numbers are growing rapidly, but it's still a lot of data to manage. Our pipeline features a number of transformations that require lookups into existing data state, which means that processing time for new records can take several seconds. Meanwhile, callers expect sub-second response time on their posts. We also deal with bursty traffic, and we need to provide consistent response times despite inconsistent volumes. So let's talk about some of the things that are important about solutions in this space. First for us is immediate durability. We want data to be stored immediately so we don't lose it. No data loss, no 500s. Durability here means data on disk and on multiple disks. Durability requires robustness against common failure scenarios like bad disks or crashed nodes. Designing for immediate durability means no data loss in the event of bugs or brokenness in the processing logic because the data still exists in a fairly raw form and can be reprocessed. And processing proceeds asynchronously once that data is secure. Data pipelining is also really important for what we're doing, the ability to construct and compose pipelines. So pipelines are composed of two main constructs. The first is a cascade between services. Data pipelines cascade from step to step, which permits separation of concerns, clear ownership across separate teams, durable intermediary representations, and the cascade powers more advanced pipelines. It can be expensive. Network and disk are involved between each of these services, but the tools are there then to permit safe data flow between services and to support complex pipelines. The other construct is a fork. More complicated flows start with forks. Forking can be done in a few different ways, but they're roughly grouped into two major paradigms. You can fork in a sorting service that writes to multiple subsequent topics, and you can also attach consumers to a stream. We use both of those approaches in the pipeline we work on. There are some common use cases for forking, extracting a subset of information from the information that's coming into your pipeline, forking out to multiple storage backends, processing things in parallel, although joining streams can be a little challenging. And then in our system, the very first fork happens right after our first collection step. We process 3 different kinds of telemetry: logs, traces, and metrics. And we immediately fork so that each one of those gets written to a separate topic. So when you put those together, that's when you start to get these composite flows. This example illustrates a composed pipeline where service 1 cascades along topic B to service 2, which splits the data into topics C and D. It's pretty easy to see how you could build lots of different pipe with these basic constructs. It's like Legos with microservices, right? Or you could put a bunch of forks and cascades in there, and it starts to look like a railroad switching yard with lots of data stores and lots of derivative or enriched data. In many ways, composable pipelines are the key feature of streaming design. But another reason to love streaming design architectures, or take one of those words out, is easy scale out. Maybe you know the distinction, but it took working in high throughput environments for me to learn that scaling out means adding more machines with fairly modest resources, while scaling up means replacing machines with new machines that have more resources, right? So as long as you can buy a big enough machine, and AWS will sell you some pretty big machines, both approaches will work. However, they cost very differently. Scaling out costs grow in a near linear fashion. You lose some juice due to the distributed systems overhead, but good algorithms do a lot to mitigate that. When scaling up, costs grow superlinearly, maybe even geometrically. Those big machines AWS sells you will definitely impact your COGS like a sledgehammer on clockwork. Consequently, most organizations prefer scale out, but multiple systems means distributed systems, and distributed systems are hard. Fortunately, Kafka and other streaming platforms provide tools for solving many of those problems without having to implement the raft algorithm yourself. In DB-centered apps, there are 2 ways that they try to scale out instead of up. Both of those solutions have problems, though. One common pattern is to scale up just your writer node and then attach a bunch of read replicas. This pattern relies on pure reads being a significant source of load. For us, that doesn't really work. Our writes are many, many times more traffic than our reads. But those reads are important when you need them. Right. Furthermore, that large writer is expensive. You are partly scaling up even as you're trying to scale out. Sharding is the other approach, and sharding routes incoming reads and writes to the correct database based on some kind of partition key. There are some downsides to this too. The main one really being that shard management is hard. It's hard to balance. When one of those databases gets hot, when it starts growing beyond the bounds, you have to find a way to shift that data to a new shard. And copying that data in a lossless way that does not interrupt the ingest of data is very tricky. It's also hard to grow, because adding a new shard changes shard assignments, and now you've got to move a bunch of things around again. Data modeling is also challenging in a sharded arrangement because many operations become very expensive. Joins often involve multiple databases and transferring lots of data back and forth between them. Aggregations can also require overfetching data and computing in the sharding service. Even in purpose-made distributed databases, like we use a lot of ClickHouse, these penalties still exist. And it can be really tricky to add a new shard to a ClickHouse database. And when you do joins, it likes to push a ton of data to every one of the shards. So when you're working in a streaming environment, they bake in the sharding through their partition concept. Producers will write messages to partitions based on a configurable algorithm. Frequently, random assignment is often better than trying to do this yourself. Consumer groups also will then assign the partitions to the consumers within the group. And consumers in this context can be a process, a thread, or a hybrid of both, but each consumer will work on one or more of those partitions by itself. All the consumers within a consumer group are expected to work in parallel on the same stream, but each of them has its own set of partitions. By dividing the traffic into more partitions than you immediately need, scaling out becomes easy. You add more consumers and distribute those shards across the consumers, and now you've got more processing power. Ideally, you pick partition counts that are highly composable numbers early on to maximize the possible configurations of partitions to consumers. But adjusting partition counts, it requires repartitioning, which is not automatic, but it's typically much easier than rebalancing a sharded RDBMS. Typically, you cascade onto a new topic with more partitions until you can turn the old one off. The fourth feature we want to talk about is the event-driven processing model. Way back at the start, we showed an example of a DB-centered architecture with services that load data from the database, transform, and then write it back. Those are polling jobs, and the polling jobs query a database, then take action on results. Polling can be hard because tuning polling intervals is difficult. Furthermore, it's difficult to parallelize a polling job without some kind of shared locking mechanism. Event-driven processing is an optimized example of polling against a sharded database. Topics are roughly tables, partitions are roughly shards. It's not really the same though, because records in a stream are in in-sort order and they're only accessible in that order. But that also means there's no overhead from additional indexing or query support. The event-driven style retrieves records by waiting until data is available versus the typical polling architecture, which just fires requests at the database to see when something shows up. That's a lot of theory, so let's look at an example. Our sample program extracts some pieces of incoming user records for use in other systems. Using these derivative records keeps the PII out of the parts of the system that don't need it. We'll use a streaming approach to process the records and split out the safe data. And that doesn't look right. Oh yeah, it is. The initial pipeline streams records into secure storage. That's our starting state. And the forking service that we're going to talk about strips the PII and writes it to a new topic.
So as Jeff mentioned, we're going to assume that we have a Kafka topic that has user data in it, specifically user objects, which we'll see in a minute. If you want to follow along, all three of the examples that I'm going to give are available on GitHub here, if you want to follow along locally. Give me a second to find the code here.
What am I? Oh.
Oh, right. I need to be mirroring.
Right.
There we go. You all see that? Okay. So we're going to start off with, as Jeff mentioned, a simple Kafka stream. It's going to consume the topic that has user data in it, and it's going to write out a stripped version of that user data. We're going to start with some configuration. Jeff mentioned consumer groups, so we need to give Kafka our consumer group name. That's how it's going to know which partitions to feed us. We're going to tell it where to find Kafka, some concurrency limits, etc. Source and target topics. I'm also going to show some just basic data classes. This user class is what represents what's being consumed, so the source topic. User ID, name, email, some PII, as you can see. We have a cleaned user object with that PII data stripped out and a method that does that work for us. Down here at the bottom, we also have some surdays. So this is how we're going to tell Kafka Streams how to serialize and deserialize our data. And here's the stream itself. This is a simple Kotlin class. It's got some setup and teardown methods. Some methods to join together our configuration that's wired up via properties. And the important bit here is the get topology method. So here we build a Kafka stream, which is going to look a lot like iterating over a collection or a sequence. We tell Kafka Streams, hey, this is where we want you to source our data, and this is how we want you to deserialize it. We're going to filter out null values. Potentially, it's upstream as a compacting topic, and maybe it sends null values. We'll get to that later. We're going to do our mapping here. So we start with a user object. We end up with a cleaned user object with all the PII data stripped out. Of note here, we're keying this. So we're providing the user ID as the key to Kafka Streams. This is going to be important for our next example as we write this to a compacting Kafka topic. And finally, we tell Kafka Streams where to send this data. So we give it the target topic, tell it, again, how to serialize it. And this is the whole code block that you need, essentially, to consume our user objects and write out our cleaned user objects. I'm going to quickly show our unit test here to cover this, that this is working the way that we expect. We use the topology test driver library from Kafka Streams. It's very handy. It basically runs Kafka in memory under the covers so that you can feed data in, query data out, and validate that it does the right thing. We're going to tell it how to configure our input topic, our output topic. We're going to create a bunch of dummy data. So here's some example users. We're going to pipe those users into our source topic. We're going to run the Kafka stream that we saw and fetch the results back out. And then we're going to validate that the results on the other side are exactly what we expect. So when I run this, you can see cleaned user objects came out the other end of our pipeline with no PII data in them. Now, forgive me, I'm going to have to switch back and forth a few times between the code and the slides. So it might be hopefully less tricky than the last time. Great. So we're going to make it a little more complicated now. We're going to talk a little bit about compacting topics, which I brought up briefly in the previous example. So we want to make these clean user records available to other teams in our organization, other services that might need that data. So what we do is we write these to a compacting Kafka topic. So what is a compacting topic? Traditionally, Kafka messages are written to a Kafka topic. They will exist there for as long as a configured TTL, an amount that you give it. It can be anything from hours to days. Kafka will automatically clean those up after the TTL period. Compacting topic's a little bit different. It has no TTL. So it has keys, and Kafka will automatically retain the most recent key written to a topic. So as you saw in the previous example, we were keying our users by user ID. As Kafka consumes updates for a user, it will clear out the older versions and retain the newer one. And that is really handy for distributed cache. So compacting topics are really useful for backing a distributed cache. There's a bunch of different ways to do it. We'll talk about a few of them. You can warm the cache on startup of your service, depending on the size of your data. And more importantly, it keeps the cache fresh in the background while your service is running. Any update written to the source topic, the Kafka Stream will automatically update your cache with that data. We're going to go back to the code and show that here. Thing makes me drag this every time. So in our second example, I'm going to start by showing our interface. So here is our user store. Very simple interface. You can get a user by ID. You can get multiple users by a set of IDs. You can put new data into the store. For this example, our implementation uses the Caffeine caching library. Again, you can get the data out, put the data into Caffeine, and it will all happen in memory. Here's our second stream example. All of this is going to look familiar until we get down here to the topology itself. Some key differences you'll notice: don't filter null values. Since this is a compacting topic, if someone wants to delete a user, they're going to write a null value to the topic. We want to use that to delete it from our local store as we consume those. And then we just have a for each statement and use our local storage, put the data into our local storage. We also have a simple REST controller, Spring REST controller, that allows callers to make GET requests to get cleaned user objects by ID or by a set of IDs. It uses our store that we saw previously. So with these pieces, it really is that simple to provide this data from memory, no external database requests, no additional network requests. Callers can fetch this data straight out of memory. Again, we have a test. Uses topology test driver again, also uses Spring mock MVC so that we can mock calls into this controller. Set up some example user data. You'll notice this user is duplicated. It comes through twice, and that's to demonstrate the fact that as the update for the user comes in, Kafka will automatically clear the previous version, and we'll have the newer date available from the latest state of the user object. And here we make calls into our controller and validate output. So again, we can see here what our HTTP caller sees. A JSON result with, if you get by ID 1 with our cleaned user data, or if you get multiple IDs, our set of cleaned user data. And now I get to do this dance again. Extended display, mirror display.
You just, I think, undid.
Did I?
Yeah.
There it is. Okay. I need to show the notes now.
You're mirroring. You're good.
Perfect. Okay. Being a software engineer certainly does not make you good at this stuff. All right. Okay, so that was great. We have our cache data in local memory. That's a really good start. You can get pretty far that way. But what happens when your app goes viral on TikTok and suddenly you have a lot more space, a lot more storage that you need? RocksDB is a great solution for this. It's a really fast key value store, originally developed at Meta. It does a great job of balancing disk and memory utilization, so there's a very good chance if you request something from RocksDB, it's coming out of memory, depending on access patterns. Now you can scale out. You need significantly less RAM on your nodes. You just have to make sure that you have writable disks. I did it right that time, yes. All right, to start out, I'm going to show you how to set up RocksDB. So we're using the Java JNI library for RocksDB. You import that using whatever build tool you use and set up some basic configuration, as you can see here, and call rocksdb.open. It really is that simple. You don't have to install the database on your host. With this code, you're ready to go. Start reading and writing to Rocks. So we have a near identical implementation of our data store. This one uses Rocks instead of caffeine. You'll note I included the Spring profile annotation here so that we get the right storage for our third unit test. This also uses the exact same stream that we're using in the previous example. So the profile annotation is also going to tell that stream where to use it. So this will work entirely on disk with the exact same logic. So this test is essentially the same. The only difference is we call out, hey, this is our third profile, so now it's going to wire in Rocks. And when we run this, again, same output as before. The major difference being now you can scale this significantly further than you could with the in-memory example. Back to Jeff.
All right. So that's basically the content. But I just want to kind of go over what we talked about. We talked about why you should use a streaming architecture, the immediate durability of data with no transformations prior to persistence, composable pipelines that support complex flows and many destinations, straightforward horizontal scaling due to the built-in partitioning, and event-driven processing semantics that abstract away the complexities of polling and sharding. We've also talked about how streaming Kafka apps work. A Kafka cluster supports many topics, each of which contain a particular type of message. Each topic has many partitions, and messages are assigned to partitions via configurable algorithms. A service subscribes to a consumer group, which distributes the partitions amongst all its members. And the service consumes messages from the topic, transforms them, then produces them to the next topic or to a data store. And we've also talked about how and why to use compacting topics. Services can write to any broker, which gives us multiple writer nodes. Services manage a local cache of the topic's contents, giving us multiple reader nodes. We warm the cache by reading the topic from the start, and then maintain the cache by reading updates. You could use that cache to back an API, or you could use it to merge streams together by enriching another data stream. So hopefully this gives you a solid foundation for introducing streaming approaches into your data flow.
And thank you for coming out. I know it's one of the last talks of the conference, so this is the crowd with endurance.
For real.